Hey there, my name is Alejandro. Welcome back for day 327 of me doing Daily LeetCode Challenge with 31 years worth of green contributions here on GitHub. So today's from us for June 8, 2025. And without further ado, let's get straight into it. Okay, what have we got today? Okay, today we get LeetCode medium from 386 lexicographical numbers. I see we've done this before, so let me refresh that definition. We solved this. When did we solve this? September 20th, 2024. Likely a Daily LeetCode Challenge of the past. Okay. Given an integer n, return all the numbers in the range 1 to n sorted in lexicographical order. Oh no, not this problem. You must write an algorithm that runs in O of n time and uses O of 1 extra space. Oh, I remember this being so annoying. Yeah, because of 1 and then 10 and 11. Oh gosh. I remember there was also a trick to this. Oh boy. Yeah, because basically you can just do return sorted range 1 comma n plus 1 key equals lambda num string of num, right? Something like this. Alright, like this is the one-line solution. Yeah, so this works, but since it's not the of n solution, I won't press submit, and get the daily challenge token, just because it must be done in O of n time and O of 1 extra space. Ah boy, okay, yeah, that's why this thing is gonna have such a high acceptance rate. It's gonna be very, very trivial to do it that way. Yeah. Okay. Oh boy. It's 1, then 10, then 100, then 1,000. Yeah, so what is always part of the solution? Oh, I remember there being some trick to this thing. I remember my friend Noor did this in a smart way when he did it. I just remember this problem being very annoying for me. Oh gosh, okay. There's only like 10 at each level, right? I can't do log n on the size of the numbers every time. Yeah. Like I can't use an array that I keep joining even though there's like at most 5 digits, right? Because it's log base 10 of n, which would technically be n log base 10 of n, not O of n. Oh boy. You could also work backwards. Right, I remember thinking of this as a tree, right? You have to do it in terms of like, solve each digit, right? Like solve all the ones, then solve all the twos, solve all the threes, the fours, For the ones, it's like for each one you have 10 options, right? You can put a 0, a 1, a 2, a 3, all the way up to a 9. For each of those you have 10 options, blah 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 blah. So you almost want to do like a Yeah, if you think of it as a tree, what you want to do is an in-order search, right? You have a tree where you have like, you know, the 1 here, and then here's like you have your 10, you have your 11, you have your 12, 13, 14, 15, all the way up to 19, and here's like where you have your 100s, all the way up to, you know, dot dot 109, and this one will have, you know, 101 dot dot 110 to dot dot 119, and dot dot dot, you know what I mean? So it's like, you know. So what we really want to do is like an in-order search, right? Where it's like we want to start with 1, and we want to go to 10, we want to go to 100, and so on, and do like a leftmost search of this binary tree, right? Now the relationships go as follows, right? Here you multiply by 10, right? Because we gotta remember we only need to use our 1 extra space, so we need to have like this tree be like something fictional in our brain. Fudge, man. Okay. Which is okay, right? For now, focus on just solving for numbers that start with 1. Everything else will be much easier. Handling begin with afterwards, right? Well, so am I lagging? I hope that I'm not lagging like crazy. Yeah. I will say base is equal to 1. While true. Yeah. No extra space, but it's fine to have. Right, and 2 times 10. It's like the pattern is like you wanna, each time you wanna go down a level. It's like doing a BFS that will end up having O of n memory inside of it in total, but at every step of the way is O of 1, count as O of 1 extra space? Probably not. Maybe like the way I need to create the function is like recursively, right? But then it's like the recursive call stack. How do you do this in just O1 extra space? O1 extra space is kind of an annoying requirement. Extra to the n numbers that you return. Because I must, so basically, yeah, like they really love for you to do things iteratively. Like the point is I want to multiply num times 10, handle it there, and come back. Wow. Yeah. Alright. Like what I want to do is something like this. Self.n is equal to n. And def backtrack num greater than self.n. Right? Otherwise we'll say yield num num times or equal to 10. Range 10. Yield from backtrack is equals and this might actually now give me a list. Oh gosh, come on. Yeah, this might actually not give me a list. Yeah. Here we'll say list yeah, this is actually good. Right, but does something like this count as over one extra space, right? Because that's what I'm trying to wonder. Res equal to this. Base digit in range 9 plus 1. Res that extends. Self dot backtrack. Base digits. Return res. My computer's laggy. I really hope that means I'm not frozen in this camera. Yeah, so this works. We can submit. And there we go, bada bing bada boom, completion streak 327 days, consistency is key, see you tomorrow. Now the only thing is like, okay, wow. First of all, that's slow as hell. Yeah, well this might be nice. This is not cool. Here we can do self.res.append num. We'll say this, right? There we go. Okay. Submit. Okay, at least we're a little faster. How do we get to that peak? Maybe we put this up in here. Boy, is this slow. So this up here. Okay. And my computer's quite laggy. Okay, how about now? 75 ms. We're still over here. People are still doing this in a faster way. Can we do this iteratively? Right, the same way that I can do DFS recursively or with a stack. How can we use... The thing is, I don't like the idea of a stack, right? Because it's like, is there one extra space? It's going to be like log n extra space. Right, like Python has no tail recursion. Like, can this be considered over one extra space? Oh, so things like lists that are referenced, you can use them like this in a function, but not... Ah. Ah, that's where the non-local comes in, isn't it? Yeah, I just learned something about Python. Yeah, stuff like lists is given by reference, so that's completely fine, but variables like integers is not the case. Yeah, it's still super slow, but my computer is also lagging like a truck, so I don't know if this is the cause, but I'm guessing not, because this is probably LeetCode server is running this to make it fair, right? We can just do res at append none. It's fine. Trying to think of how to do this in a better way. So I want to do like a DF. Like, thing is, you can't avoid it, right? Like, I might be able to do things with a stack. Backtrack, I'll take a none. Yeah, here we'll do something like this. Stack will initially have 9, 8, 7, 6, 5, 4, 3, 2, 1. because we always pop from the end of the stack, so we'll evaluate the ones first. Right, here we'll say while stack. Stack.pop. If num greater than n, continue. Right, otherwise it's not, so res.append n. Because I don't know how to do this without like a stack, right? Or res.append num, sorry. Here we'll say 10 0 equal to 10. For next num, num plus 10, num less than n, stack.append next num. But that means we'll put the biggest one first. So what we want is num plus 9, num minus 1, negative 1. Return res kind of a thing. Okay, that works. Let's submit. $66 ms. A little bit of an improvement, but not the biggest. Greater than n. So we go to n. And do this. $35 ms. Okay, we're getting closer. Okay, so we can delete this. Greater than n. Continue. Submit this. Ooh, there we go. 11 ms beats 72.66% of submissions. That is just wonderful. Okay. Okay, sweet. Yeah, there we go. We solved it. The only thing is, yeah, for the over one extra space, I don't. It's not, right? So you start off with 10. You might have 10 more, but it's like this stack will end up having. Like, I'm gonna have 2 times n total extra space, right? Like this will have n elements, and the stack in total will have processed a total of n elements, right? Yeah, I'm just gonna assume that it's kind of okay, right? It's not an unreasonable solution. So we'll just leave it as that. And yeah, okay. So nevertheless, as always in my videos, I do a quick recap of how to solve the problem. So for this one, given an integer n, we want to return all the numbers in the range 1 to n sorted in lexicographical order. So basically, if they were strings, right, return them in that way. So for example, one way of solving this problem will be return all the numbers. So do the range from 1 to n inclusive, so n plus 1. And the key will be look at each number, so lambda num, and take the string of that number, right? So sort all the numbers based on their string representations to get them in lexicographical order, and something like this will definitely work, right? Here we'll get an accepted. Here we can submit something like this, right? And wow, it's an efficient solution. ms beats 100%. Wow, so the n log n way is actually faster. That I did not expect. Okay, that's kind of funny. All right, but we have an O of n way that happens to be a little bit slower. That's actually kind of shocking. Goes to show you how beefy and juiced up that Python sorted function really is. But yeah, so we really are 11 MS speed 72.66% because you must write an algorithm that runs in O of n time and uses O of 1 extra space. Now for the O of 1 extra space part, this is where it's kind of iffy. Obviously, you need O of n space to return all the numbers in the range of 1 to n in sorted fashion, so that's what this result array will be. Those will be the n numbers. And then I have a stack that initially starts off as constant space, like I end up popping things and adding at most 10 things at a time. But eventually, every single number will have been in the stack exactly once, no more, no less. So throughout the entire duration of the algorithm, the total amount of unique elements that were in the stack in total, but not necessarily at a specific point in time, is all n elements from 1 to n. I could have partitioned it by base digit and stuff and so on, but that would have just been 1/10 the space for each of the 10 runs. I'm gonna assume that it's okay. By technicality, it really isn't O of 1 extra space, so I'm not sure how to do it in O of 1 extra space, but this is a solution that is at least O of n time and not just like, the lazy O of n log n solution, so at least there is that. So the way that I solved it is, okay, basically I did a DFS of this. So the way I thought it is like, okay, first of all, think of each number has a starting digit, right? Whether it's a 1, 2, 3, 4, 5, 6, 7, 8, 9. Separate those digits, right? Solve the case for all the 1s, then solve the case for all the 2s, solve the case for the 3s, right? Because even if you have 1, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, right? This is still lexicographically smaller than 2, right? Or even 2, 0, 0, 0, 0, 0, right? This is lexicographically smaller than this number. So you might as well solve all the 1s, put them at the beginning of the array, solve all the 2s, slap them to the array, solve all the 3s, slap them to the array, right? For example, here you have all the 1s, 1, 10, 11, 12, 13. These are all numbers that start with 1, and then you have the 2s group, right? And then you have the 3s group, the 4s group, the 5s group, etc. So that's why I solved it in that way. So initially what's in my stack is 9, 8, 7, 6, 5, 4, 3, 2, 1. So the numbers in reverse order, because I'm always going to pop them in the end of the stack. So that way the very first number I pop is the 1s. So I'll end up solving the 1s first. Once I'm done with the 1s, I'll end up popping the 2 and doing the 2s, yada, yada, yada. The way I thought about this problem is like, okay, if we think of this as a tree, right, we can think of our base digit as our root, right? So our base digits are going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. Remember, those are going to be like, kind of like, we can solve the 1s, then the 2s, and the 3s, and so on. Here, just have them cleverly in my stack in this way. Then, it's like the next number after 1 will be 1, 0, right? And the next number after 1, 0 will not be 1, 1, it'll be 1, 0, 0, right? Something like 100 is actually smaller than something like 11. So if we think of this as a tree, we can think of it as we put in, the 10 numbers that are below as the children. So it's like every single node has exactly or up to 10 children, right? So this one would have like these 10 children over here, right? In this case, we have nothing more than 13, so it's like it would kind of get separated off. That's why I say at most 10 children, but for now we can just think of it as 10 children each, right? And each of these are also going to have 10 children, right? So for example, 10 will have the numbers 100 to 109. We can scoop up a bit of space here, and there we go. The number 11, sorry, my eyes. We'll have the numbers 1, 1, 0, all the way up to 119, right? And you can assume that it's kind of the same with the rest of the numbers here, right? So that's kind of the gist, and it just keeps going as much as you need to. But the point is this. From 1, the next one we want to do is 10. This is obvious. But then the next one we want to do is not this 11, it's this 100, right? So if you can kind of imagine in your head, what we really want to do is an in-order traversal of this quote-unquote binary search tree, right? Or, well, it's not a binary tree here, it's like, a 10-array tree. But you get the point, right? We want to do essentially an in-order traversal of this tree. We want to go as much left as we can, yada, yada, yada. If you're familiar with in-order traversals, you'll know what I'm talking about. So there's pre-order, post-order, and in order. Here, you actually don't want to do, this is not actually in order, right? Because the thing is, like, when you get to like a leftmost node, you won't start going as much right as you can. No, this is in order. Yeah, no, this is in order. You'll want to do all of these. Now, yeah, I'm confusing myself for no reason. Pre-order just means you pass by everything first. Why am I confusing myself? If you have a binary tree, if you have 10, here you have 5, here you have 15, here we'll call this 5, here we have 9, 3, right, 1, 4, then in order will be, oh no, in order means you go left and then you print the 1. Okay, sorry, so we're doing a pre-order traversal of the numbers, right? Okay, that's why I was confusing myself. We're doing a pre-order search of the numbers. So it's like when we go to 1, we lock that in, right? We go to the 10, we lock that in. We go to the 100, we lock that in, right? Because that's kind of the order that things are supposed to be. You don't try to go as deep as you can on the left and then, you know, stop there and go to the right, yada, yada, yada. You're doing a pre-order traversal of this quote-unquote ternary tree. Okay, so now that we have that cleared, that's essentially all that I'm doing. And at first I did it with a function I call backtrack because, you know, DFS, pre-order traversal, very easy to implement recursively, but I deleted that and decided to do things recursively. And I can kind of show that. While stack, what I'm going to do is, okay, pop the number from the stack. In this case, I'll start off with 1, so I'll essentially solve the ones group. Here's just like, okay, if the number is greater than n, remember we only want numbers in the range from 1 to n, so we just kill it, right? If n is greater than n, we ignore it. Otherwise, we're going to append this number, right? In this case, like, you know, we're appending 1, so what our res would look like is it would have 1 now. And then we're going to multiply the number by 10, right? So here's like our number is now going to be equal to 1 times 10, which is equal to 10, right? If num is greater than n, continue, obviously. Then we're going to say, okay, for next num in range, num plus 9 minus 1, negative 1, what the heck does this mean? Well, the point is that here, when we have a number like 1, what's the next step of the tree, right? Here, let me undo so we can go back to the tree. It's like this, right? Then the next phase is to have this 10, right? So we need to multiply this number by 10 to get to that phase, right? And it would be the same. If this was a 2 as a base digit, this would be 20, this would be 21, this would be 200, this would be 209, this would be 210, this would be 219, right? It would be the same exact thing. So that, like, each base digit is going to have the same logic. I'm just doing ones because it's the beginning one, right? So we're going to have to multiply the number by 10, and then we need to have all, 19 sub-children. But we're first going to go through this one and so on, so I'll show you how that goes. So what we're going to do is if we have a number like 10, we're like 1, we're going to multiply it by 10, so we get to 10, so we're essentially at this child. And we say, okay, we need to add all these children to the stack, right? But the way I'm going to put them is I'm going to put them in reverse order. I'm going to put 19 first, then 18, then 17, then 16, 15, 14, 13, 12, 11, and 10. So that's why I'm going to go from 9 plus 9, right? So 10 in this case, 10 plus 9 would be 19. So I add 19 first, 18, and so on, and I just keep on going until num minus 1 non-inclusive, i.e. until num, which is 10 itself. And I just keep adding those onto the stack. Actually, I realize now that I probably don't need, I can do some optimizations after. The point is I'm going to put them in the stack in reverse order. That way what's at the top of my stack at the end of this for loop, right, is 10. So that way 10 is going to be the next one I process, right? So when I go back into my while loop, I'll pop 10 from the top of my stack, right? And then I'll start looping through all of 10's children, right? Which will be 100 to 109. And for each of those, I'm going to put them in reverse order. I'm going to put 109 first, 108 first, 107 first, 106, 105, 104, 103, 102, 101, and 100, and then go on with the while loop, and then 100 will be at the top of my stack, and I'll explore those, right? The way that I don't explore things infinitely is that whenever I see that a number is greater than n, I decide to continue the for loop, right? I do not keep going, right? So if num is greater than n, that means like I went too far, let me stop and stop for this number, right? So I only ever append things into res that are like, between 1 and 10. And that's kind of the gist. Once you're done with this for loop, then at the end you just return res, and there you go, bada bing, bada boom, you have a nice and working efficient solution. I can do one more optimization here. Oh no, I'm gonna need to. Yeah. Here we can just do something like this. If n, then 10, range of 1, n plus 1, right? Otherwise I have at least all 10 numbers. List of range of 1 to n plus 1. Yeah, and now we'll have these, and now I can essentially probably get rid of this, right? Right, so something like this will work. I guess it's the same time complexity. Yeah, and now I can't remove this, right? Otherwise I'll get wrong solutions. Yeah. Yeah, okay, I'll just leave it as how it was before. Just, yeah, I mean, like, this should save me time. Right. There we go, 7ms fits 95.08% of solutions. That's exactly what we love to see. And yeah, but otherwise, that's pretty much in terms of how I was able to solve this problem. So otherwise, that's pretty much it for this video. If you did find it useful and enjoyable in any shape or form, I'd highly appreciate it if you left a like or a comment. Well, otherwise, I'll catch you next one. So till then, ciao, ciao, my friend. Bye-bye.